Module 9.8, the Pythagorean scale. Let's say you have two strings of equal length and tension. If you divide one string in half, you'll get a note on the divided string that is an octave higher than on the other string. You'll have a frequency ratio of 2 to 1. When both strings are played together, the sound will be harmonious or consonant. Now, divide the original string into thirds. Its frequency will be 3 times that of the original string, and it will have a 3 to 2 frequency ratio with the string divided in half. You've now created an interval known as the perfect fifth. When you play both strings together, the sound will again be harmonious or consonant. Now, divide the second string into fourths and play it with the string divided in thirds. The resultant frequency ratio is 4 to 3, which creates the musical interval called a perfect fourth, another consonant interval. Pythagoras found the ratios of 3 to 2 and 4 to 3 so harmonious that he decided to create a scale that would have the largest possible number of perfect fourths and fifths. So how can we do this? We will choose the frequency of notes in what is known as the circle of fifths. So the notes would be C, G, D, A, E, etc. With each interval of a fifth, we should make the frequency ratio exactly 3 to 2. Now, if we do this starting on C, this will eventually get us all 12 notes of the chromatic scale. But doing it this way, a very unhappy thing occurs. The note C4, an octave above C3, is not double the frequency of C3. 262 Hz times 2 is 524 Hz, not 531 Hz. So, we can use a little trickery to fix that, if all we want is the major scale, which is C, D, E, F, G, A, B, and C. So, let's make F3 4/3 of C3. Why? C3 to F3 is a perfect fourth, C, D, E, F. And the perfect fourth has a ratio of 4 to 3. Then F3 to C4, F, G, A, B, C, is a perfect fifth with a ratio of 3 to 2. If we do 4 to 3 times 3 to 2, doing the math, that ends up being 2, making C4 a perfect octave above C3. Then all the other notes, D, E, F, G, A, and B, can be made by 3 to 2 ratios, or 3 to 4 ratios to keep them within the octave. 3 to 4 equals 3 to 2 divided by 2, and dividing it by 2 brings it down an octave. Now, this gets us a lot of nice fourths and fifths. And if you're singing a lot of Gregorian chant, which is voices moving together in the interval of a fifth, you're in great shape. However, most musicians are not restricting themselves to Gregorian chant. Without diving deeper into the math, here's what the other intervals look like in the Pythagorean scale. C to D is a 9 to 8 ratio. This is dissonant, but intervals of a second are not consonant in any temperament. C to E is 81 to 64. This is the interval of a major third, a very important interval for standard musical harmony. 81 to 64 is not a ratio of small integers. If the top number was 80, the ratio would be 5 to 4. So it's close to being very consonant, but will have a bit of beating. C to F is 4 to 3, perfect fourth, it's good. C to G is 3 to 2, a perfect fifth, also great. C to A is 27 to 16. The major sixth is also an important interval, but in the Pythagorean scale, it is not a ratio of small numbers. This interval is fairly dissonant in the Pythagorean scale. Finally, C to B is 243 to 128. not consonant, but sevenths are not consonant in any temperament. So, if we want to have nice major and minor harmonies, what's a mother to do? We'll look at two possible solutions in the next two modules. To review, consonant intervals will have frequency ratios that can be expressed as ratios of integers less than 9. The Pythagorean major scale is built on perfect fifths having frequency ratios of 3 to 2. Harmonically, fourths, fifths, and octaves are harmonious in a Pythagorean scale. Harmonically, thirds and sixths are not consonant in a Pythagorean scale.